Final session,
to go back and check
kick
how
it
the
off.
bottom
We have Douwe Jan Bonthuis, who's going to tell us about ions and charged surfactants and aqueous interfaces.
Yes, thank you very much.
Okay, this is supposed to be working, I think. Good. So let me start off by thanking the organizers for inviting me here. It's been a very nice week so far. Learned many.
I don't think it's on.
Is it not on? Is it? Maybe a little bit further up, like this. Yeah, it's on. Okay, I'll try to speak up a little bit then. Yes, so it's been a very nice week. Learned many new things this week. It's been very nice being in Cambridge here. So I'm from the Institute of Theoretical Physics at the TU Graz, where I moved actually very recently from the FU Berlin, where I did most of the work that I'll be talking about here. So I'll first briefly explain the type of systems that I work on and the type of work that we do. So I'm mainly interested in aqueous interfaces. So as soon as you have systems in water, you have many interfaces between the water and the colloids or the objects that you put in water. And some of the systems that I work on is vesicle and colloid transport. So this is an example here of vesicle transport where we have these vesicles, so basically a lipid container, which transport biological molecules and ions and water in this Golgi apparatus. So that's one thing, but where the question is of what's exactly the physical mechanism by which these vesicles transport objects throughout the biological cells. Then at a smaller scale, so if you look really closely at these membranes, in the biological membranes there are all kinds of small pores, typically formed by proteins, but also many other mechanisms. You can make small pores in membranes, and they transport water and ions at a very high rate and very high sort of really atomic specificity. And again, the question is, how does that physically really work? Now, these systems can be mimicked in devices. Yeah, you can design systems that behave in similar ways. So that brings you to these nanofluidic devices, for example, made out of glass and polymers. We have transport of objects through these channels, and again, you can go to these really molecular scales. So this is a picture from my collaborator Liederik Bouquet, who has a system where you can take a single carbon nanotube on an AFM and embed it inside a glass membrane to measure transport really through a tube of only several nanometers wide. So what these systems have in common, and the main thing that I work on, is that they have aqueous interfaces. Yes, so you have water at these surfaces, and water has a rather peculiar property. I mean, it's an anisotropic molecule, right? It has two positively charged hydrogens and a negatively charged oxygen. And in bulk, these things it's homogeneous and isotropically oriented. But as soon as you introduce an interface, you have this structuring. So the water forms layers, very high densities and small density caps in between, and it orients. And so typically, water molecules orient with their hydrogens pointing towards the interface and the oxygens pointing away. And this is a very profound influence on the behavior of the entire solute, of the entire interface in the water phase. So it has an influence on the dynamics, but also on the interactions between these surfaces. So when you want to study this, there are a couple of very nice experiments that you can do. And one of them, sort of one of the oldest ones, is an electrophoretic experiment. So what you have a colloid in water, which is typically charged. So in this case, negatively charged. You apply an electric field, and then clearly, the net force on this system, because it's a charged colloid with a cloud of counterions, so the net charge is 0. But because you can induce some shear in the interfacial layer, and that's what actually drives the colloid, right? So so the counterions will be pulled to one side, the interfacial layer will be pulled to the other side, and just by this shear, you actually move this particle along. So that's a relatively common experiment. This has been done for many years, and it's still being used a lot in biochemical research. But for me, that's still a little bit complex because there's a direct interaction, of course, between the colloids and the water and the ions. So what I will do now, and the main thing I'll be talking about today, is just leave out the colloid. Yeah. So now we look at a vacuum sphere, an air bubble in water, and you can still induce a non-zero electrostatic mobility here. As long as you can induce some shear in the interfacial layer, you will be able to actually move this particle along. And that's what happens. So this is an experiment. First time it was observed in 1861 by Quincke. So this is a glass cylinder. There's an air bubble inside here, and there are two electrodes. And you apply an electric field, and you see the air bubble actually moving. The image is actually from 1914, because in 1861 they were apparently not able or not willing to put pictures in papers. But it's clear. So this air bubble actually moves to the positive electrode, so it behaves as if it was negatively charged. And the question is why does it behave like that? There are two possible explanations for this that I will be treating. The first one is absorption of ions. So as soon as you have charge stuff absorbing on the surface, you can induce a shear in the interfacial layer. And the second thing is a mechanism that has been suggested many times over the past century, is that as soon as you have these oriented water molecules, you do not have free monopoles. You do not have any net forces on these particles, but you can, as soon as you apply an electric field, you do induce a net torque density because of the orientation of the water molecules. And the question is, does that lead to any non-zero electrostatic mobility? Right. So before I continue, I think this is a good moment to include a little disclaimer. So I do not design anything. Yeah? So the things that I work on exist already, and it's and these are certainly also not new materials, right? I mean, many of the experiments that motivate my research and that I work on have been performed more than 100 years ago. So so in that sense, it may seem a little bit out of place, but I hope to convince you in this talk that it's actually the interfacial layer, so that is 1 nanometer at the interface, that actually has a very big influence on the behavior of these objects in water. So as soon as you have any systems in water, whether it's colloids or microtubules or any sort of polymers in water, then the interaction is dominated really by this first interfacial layer of only 1 nanometer wide. So the systems that we've seen many examples of this week, I think it is important to think when you really want to look at the interaction to take this sort of interfacial effect into account. So this work has been done together with a few people that I would like to thank here. First, Yuki Umatsu, who did a postdoc with us. He's now at ANS in Paris. Secondly, Shavkat Pamatkulov, with whom I've worked together for a long time, who is actually a proper material scientist. He's the director of an institute in Uzbekistan that operates a giant solar furnace, which was used in Soviet times to optimize materials for rockets. There's Roland Netz, who many of you know, and Christopher Lolio did a postdoc with us. He's now in Jerusalem. Right. So I'll first. So now I'll go through these two different explanations that I showed you. Two different ways of inducing some sort of an electrostatic mobility for an uncharged solute, for an air-water interface. And I'll first look at this idea that if you apply an electric field, you induce a torque on water molecules, and that without any free charges, you can still move it. Right. So the idea is, so how that would in principle work is the following. So you apply an electric field, your water molecules are oriented, you induce a torque, and that torque gives rise to a spin field. So on top of the usual velocity field, we now have a spin field in the fluid, and this we can take into account on a continuum level. So what we do is we extend the Stokes equation, now allowing for an asymmetric stress tensor. Yeah, because the particles are anisotropic, the stress tensor is allowed to be asymmetric, and it gives rise to an antisymmetric part, and this is the dyadic factor of the antisymmetric part of the stress tensor. Yeah, and the rest is the usual Stokes equation. So we have a velocity u, a pressure, and a viscosity. Yeah, so that's the conservation of linear momentum. And then we continue with the second equation, which is the conservation of angular momentum. Yeah, so we have the moment of inertia of the water molecules. The spin field is here. Then we can induce some torque. Yeah, so that's the gamma is the torque that is produced by any sort of field that we apply. And then we have here, we have two friction terms, or at least one friction term, which is the spin stress tensor C, which depends on the gradients in the spin field. And then here's the coupling term. So that's the term that actually couples the vorticity of the fluid to the spin field. Yeah, and that's the same antisymmetric stress that comes in there. So for this we can write down two material equations. So the easy one is the spin stress. So as soon as we have gradients in the spin field, we'll have some form of friction, which is parameterized by this spin viscosity nu. And here's the coupling term. So that contains the vorticity, nabla across u, and it contains the spin field. Yeah, so as soon as you have exactly the right spin for the vorticity, then effectively your entire fluid is rotating and you're not dissipating anything. But as soon as there's a mismatch between your vorticity and your spin, then there is some dissipation parameterized by this viscosity eta r. Right, so these are sort of the constitutive equations, and then we need to go a little bit further to actually calculate this torque, and then we can solve this for the system that we have. So this we did. You can do it in many different geometries and many different assumptions that you make. But I think the most general and most important one is where we take a geometry. Yeah, so we have three directions: x1, 2, and 3. 2 is pointing into the plane, and we apply a constant electric field, and then we need to calculate the torque, and we calculate it from a time evolution equation for the dipole density. And you get an expression like this. Yeah, so this is what comes out for the torque. Yeah, this is combined the top equations in this geometry, where the subscripts 2 and 3 refer to these different directions, 1, 2, and 3. And as you can see, so C is an integration constant we don't need to care about, and the torque actually depends quadratically on the applied field, E1, 0. This E3 mu is the field coming from the orientation of the water molecules, and it all depends linearly on omega. Yeah, so it means that there is one solution for omega equals 0, which is the solution of minimal entropy production, so that's the stable solution that we have, and it depends quadratically on the electric field, so that means that you will never be able to actually induce any torque. Yeah, so there are two arguments that you can see immediately that this will never work. Yeah, you will never be able to get any non-zero mobility out of a pure dipolar fluid. So that's I think a nice calculation, because this mechanism has been suggested many times, and it's still actually being published occasionally that this works. I mean, if you do for example an MD simulation, you can easily produce some sort of a mobility out of nothing. So that's still occasionally papers come out that actually claim that this is possible. It's not. It's definitely impossible. You need some sort of a charge separation in order to produce a non-zero mobility. So that's the next thing that I'll be talking about. So here the idea is that you have ions from the solution adsorbing preferentially on the surface. Right, and as soon as you have a difference in affinity of the ions for the surface, then you will be able, you get a charge distribution in the interfacial layer, and as soon as you apply an electric field, you induce a shear there, and that can actually produce a non-zero mobility. And they're very nice. Of course, what you need to know is what is exactly the affinity of the ions for the surface. And this is what is very nice about it, is that you can measure this directly in an experiment. And again, these experiments are really relatively old, because there's an expression this you derive directly from the first law of thermodynamics, the Gibbs isotherm, where you have a change in the surface tension, the gamma, so that's the total change of the surface tension with when you change the chemical potential, and it depends on a sum over the species I, so these are all different species that you have in your system, over the excess, and I sigma, so that's the number of particles of species I which is sitting at the interface. So sigma denotes the interfacial layer per unit area, and then multiplied by the differential of the chemical potential of these particles. Yeah, so this you can rewrite in terms of the concentrations. you get a term that is roughly equal to 1. Yeah, it's very close to 1. This is again the surface axis, and this is the now the concentration. Yeah, so you can easily measure this by taking a solution, you change the concentration of some species, and you measure the change in surface tension. Yeah, that's a relatively simple thing to do. And the surface axis is, I mean, you can write it down like this. Yeah, so we have a surface axis where I now only runs over the positive and negative ions, and we take out the water species, which is of course present, by defining a position, the Gibbs dividing surface, which is the position where the axis of a water molecule is absolutely 0. Right, so that we only need to care about the ions there. Yeah, so then the axis of the ions is given by an integral from -infinity to the Gibbs dividing surface over the concentration on one side, and from the Gibbs dividing surface to infinity of the bulk concentration minus the concentration of ions. Yeah, so what this gives you is, maybe it's good to draw that because I'll be showing a few of these pictures, is if you now measure the surface tension, or the change in surface tension from the 0 concentration limit, here's 0, let's write here delta gamma. That's the thing that you measure as a function of the concentration that you add. Then if the thing goes down, then because of this minus sign, oopsie, oops, there we go. Because of the minus sign here, that means we have adsorption of this species. And if it goes up, then we have desorption. Yeah, so this is a depletion, let's say, of ions, and the other one is adsorption. Yeah, so this is there are no approximations here. This is directly from the first law of thermodynamics. You can do a simple measurement, and we know which sort of whether ions adsorb or desorb. And these are these measurements performed in 1877 and in 1899. So this is not a typo, right? This is really these measurements were done then, and they're surprisingly accurate. Yeah, so if you now look at the modern measurements, they're sort of spot on the right values. So here is the change of the surface tension as a function of the concentration for different ion types, for different salt types. And what you can see is that most ions are repelled from the interface. Yeah, so that's a depletion. Ions stay away, and that's in line with a theory that was developed much later, actually in 1936 by Onsager and Samaras. That you have an image charge repulsion which keeps the ions away. Yes.
You said that you did no approximation, but actually you took the ideal part for the chemical potential.
This bit you mean, right?
Yes.
Yes. Yeah, that is that's in there. Exactly. Yeah. So I plotted as a function of C. I could plot it as a function of the chemical potential. That would have been more accurate in that sense. Yeah. So that's an approximation. But
Assume very low concentration.
Yes, but it's still close to 1, even at relatively high concentrations. Yeah. So it's yeah. But that's in there. Yeah, you could rewrite everything in terms of the chemical potential, and then there's no approximation there. So what I'll be showing here is mainly really adsorption or desorption. So it's either going up or going down, and this will not be influenced by this term, right? So so it will not change the sign. It might change the magnitude a little bit, but in terms of whether the particles adsorb or desorb, there's no approximation here. Okay, but there's one type of salt, so the acids, which behave very differently. Yeah, so for the acids, the surface tension actually goes down, which means that these acids they adsorb at the interface, and this has been rather controversial even for the entire sort of past century, and it's quite funny to read. So even immediately after these things were published, there are letters being written to the Poggendorfer Annalen der Physik that it must be wrong and there must be contaminations. So I'm not sure whether in those days people already traveled to conferences to shout at each other, but they did write letters that this can never be right. Yeah, so it's really quite an amusing thing to read. But this has been reproduced many times. So later in 1899, the same thing. The acids adsorb and the other ions are desorbed. And these are different measurement methods. Yeah, either capillary rise or this drop fall method. And I have a collection of many different measurements that I collected over the sort of things that have been measured over the past century, plotted here. So this is the derivative, the gamma d00. That's the derivative of this surface tension curve for different combinations of ions. And you can see that the surface tension change is typically positive for most ions. It's very positive for the divalent ones. Yeah, so that's all very much in line with Onsager Samaras. But then as soon as you change the cation for the acid, for the H, there's a consistent shift down. Right? So it's really very hard to explain this in any other way than that the acid is actually absorbing, that the H4 plus is absorbing. And that's, of course, that is in contrast directly with what I showed you earlier, that these air bubbles, that they're actually moving in the direction of the positive pole. Right? That suggests that there's a negative ion absorbing and not the H4 plus. Yeah, so that's a contradiction, and this has been debated very fiercely over the past decades. So what we do is we now really try to see, so is there any sort of, can we get out of a molecular model, can we get this absorption of this acid at the interface? Can we explain why that happens? Can we see whether it happens at all? So what we did is molecular dynamic simulations. So this is really an atomistic model for this system, and it is relatively simple. So we only have the gas layer, which on a molecular level is simply a vacuum. We have the water and we have the ions. That's the only thing we have. And then we optimize these ions to reproduce the macroscopic thermodynamic variables. Yeah, so this is a relatively uncommon thing to do. People typically use, for example, quantum mechanical calculations or other ways of optimizing these classical molecular force fields. We optimize them with respect to the macroscopic thermodynamic variables, because in the end it's macroscopic thermodynamics that we're measuring at all. And so it's the only thing that we actually care about. We don't really care about the molecular details of this atom, of this molecule. So what we do is we take a classical model. This is a rigid model. So it has three hydrogens, one spherical oxygen. It has a Lennard-Jones interactions only between the oxygen and the water molecules. And it has partial charges, which are denoted here by these deltas. Yeah, and the partial charges we can change, and the values of the Lennard-Jones interaction we can change, but the rest we keep constant and classical. Yeah, and the reason we do it this way is because it has been very, very successful in water models to take a rigid model of two hydrogens and one oxygen that works really, really well to reproduce pure water properties. And then what we optimize for is, of course, all the interactions that we have in the system. So we have the interaction between the ions and the water molecule, right? That's one set, and we have the interaction between the ions themselves. So we have here, so we optimize these first interactions with respect to the free energy of solvation of an ion pair, and then we optimize these interactions with respect to the activity coefficient. Yeah, so as soon as you increase the concentration, you have a slight deviation from zero, and this we can use to optimize these things. Yeah, so by optimizing these values, then we know that at least in bulk, we reproduce the macroscopic thermodynamics of these ionic solutions. And then, of course, the next test is, does it actually work at the interface? Yeah, does it give us the right behavior there? And this we can do straight away. So we make an interface here. So that consists of water and vacuum. The water is sort of shown in blue here. Well, the vacuum also, I'm sorry, but so the water are the little spheres here on the right-hand side, and then we put in these ions, HCl, yeah, so H2O plus molecules and chloride molecules, and we look at the density, and you can see that the H2O plus is actually adsorbing, the Cl is desorbing a little bit. Yeah, so there is an axis here, of course. I mean, the axis of the two ions must always be the same, but they are electrostatically attracted to the H2O plus. They don't adsorb by themselves. Right, so they only compensate for the charge at the interface here. Yeah, but you can see that the H4 plus is indeed adsorbing and the Cl minus is desorbing. We did the same just to check for sodium hydroxide. So again, same type of optimization for the hydroxide. We add the sodium and we look at the same sort of density profiles. And here you can see that both the hydroxide and the sodium are being repelled from the interface. Yeah, so just for the interpretation of this graph, so this is the concentration relative to the bulk concentration as a function of the position away from the Gibbs dividing surface. So the Gibbs dividing surface is the surface where you have zero water excess, and then you have these curves for the ions in there. Yeah, so that's the way we see this. So this is nice, but it's only pictures. Of course, we can do this quantitatively because we can simply calculate the surface tension in these systems. We calculate it directly from the anisotropy of the stress tensor, which is available in the molecular dynamic simulations. It's simply right there. And we can plot the change delta gamma as a function of this concentration. for these different salt types. So sodium hydroxide, sodium chloride, and HCl. And what is shown here are the big white symbols are the simulations, and the other symbols are a collection of the data that I showed you. Yeah, so all the data that we have are given by the solid symbols here. And you can see that indeed for sodium hydroxide and for sodium chloride, the salt is repelled from the interface, so you get this depletion, which is shown here, whereas for sodium hydroxide you get this adsorption. And it's a relatively weak adsorption, right? So the molecules are adsorbed, but if you look at the actual energies, it's of the order of 1 kT. Yeah, so it's a relatively weak adsorption, but they do adsorb, and it's actually sort of quantitatively reproduced in these simulations. Yeah, so this is very, I like this a lot because it shows that if you do this thermodynamic optimization of your molecular force fields, you actually get out exactly the right behavior at the interface. So this is quantitatively correct, which I really liked. Yes.
Generally, we are close to an interface with effective electric constant. Of course, it's not defined there. It's supposed to be like 7 as opposed to 8. So is your force fields picking up these changes? Flexible force field.
Yes. So this has not been optimized for, right? Because it's because we did the optimization in bulk. But indeed, at the interface, the dielectric constant changes, and it changes in fact in very so there's an anisotropic change, we know, right? So there are two components that are very different at the interface. And that is included in the simulations, of course, because the water is right there, and it sort of gives you this weird behavior of the dielectric constant.
Water because the ions change it too.
That's true. Yeah. So it's all this is all non-polarizable. Yeah, that's true. So both the ions and the water are non-polarizable, but of course, even in a non-polarizable water model, you do have this change of the dielectric constant. And what is very nice is that if you do the optimization in bulk, it still reproduces the surface properties, even though this polarizability is not explicitly included. Yeah, I would say it is implicitly included because we optimize for the London part of the Lennard-Jones interaction. Yeah, so we change the Lennard-Jones parameters in bulk, and that should include at least part of the polarizability.
We found that the polarizable force field is important if you have sort of bromine or iodine, where this, I don't know if you had. So if you want to reproduce, say, Hofmeister series, you would have probably some problem.
Yes, well, it's really nice is that you can, by this optimization, you can actually reproduce the Hofmeister series without explicitly including the polarizability. Yeah, so it's a nice, yes.
I have a question regarding this polarizability issue because in principle, if you just have a rigid model, you would think that the image charge would pull you out of the interface.
Yes.
So then what is the mechanism that allows the H3O
Thanks. That's a very good question.
at the interface? I mean, that's what I would
Yes.
like to be. I mean, with a polarizable, you can think how that happens.
Yeah.
But with a rigid model,
Yes.
how?
No, that's a very good question because that's the next few slides. So thanks. Because this is the next thing that we looked at. Yeah. So what is actually the mechanism that drives the absorption of the H2O plus to the interface? And the first thing that we looked at is the orientation of these molecules. Yeah, so we define an angle for every molecule, which is simply the angle between the dipole moment and the normal to the surface. And this we can calculate for both H2O and H3O plus. And what we show is the average of the cosine of the angle. Yeah, so if it's 1, it's fully oriented in one direction, and if it's 0, it's fully isotropic. Right? That's the idea, and this is again the position with respect to the Gibbs dividing surface. And you can see that for H2O, we see the usual behavior. So the water molecules to the sort of the far end of the water phase are pointing with their hydrogens pointing towards the air. Right. So that's the usual behavior that I showed right in the beginning. And then it oscillates a little bit and it goes to 0. Now the H3O plus is actually oriented very strongly. Yeah, so it's very strongly oriented with the hydrogens pointing the other way towards the water phase. Yeah, so it's really sitting at the interface. And it's something that you can actually see here, right? You can because it's such a strong effect, you can actually see it happening right there. Now there is, of course, I mean, coming back roughly to the brief discussion that we had, is whether this is a real effect or whether this is an effect of having a rigid classical model. So what we did is ab initio molecular dynamic simulations. So where we really solve the forces by solving the Schrödinger equation and then do a classical time evolution. And there again we can define this angle and we can calculate the distribution there. And those are the solid symbols here. So this was done by Christopher Lolio. And you can see that also in the ab initio calculations, which are fully polarizable, and it's a quantum mechanical model of the interface, we see the exact same effect. Yeah, so if you put simply one extra proton there, and this is at 6 mol per liter, because the quantum mechanical calculations are relatively small in size, so we have to go to very high concentrations. But it's so it's clear if you simply put one extra proton, you still see the orientation of this H4 plus structure at the surface, and also the water orientation is reproduced very, very accurately. Yeah. So we believe that this orientation is actually there, right? Whether it's whether we do this classically or quantum mechanically, we do find the exact same orientation. Yes.
I guess the question of Alex is, yes. So are you gaining some entropy on the water structure by doing that? Because
yes.
There is a work of bringing the ion, which is due to the image charge that depends on the distance, and it becomes very strong if it was continuous. So it
yes.
must be entropy reduction.
Yes. That's true. So that's okay. So yes, So there's some. I mean, what we can do. So what we did is really calculate the total free energy as a function of the position for this ion. Yeah, so you simply do a thermodynamic integration. You take it and you move it, and I will give you some sort of hand waving arguments of where that free energy profile actually comes from. Maybe I can show the free energy profiles first. So they're right here, right? So this is what we calculated by thermodynamic integration. So you take your ion, you put it somewhere, and you simply calculate the forces that you need in order to pull it through the interface, and then you integrate. Yeah, so this is the potential of mean force as a function of the position for most ions. So OH minus, Na plus, and Cl minus, you see this repulsion. Yeah, so the ions are pushed away, and for H2O plus, you see this adsorption of about 1 kT. Yeah, so that's effectively what we. So that's the free energy corresponding to what we saw already. And now what we can do is we can calculate the interfacial electric field. So this is the field produced by these oriented dipoles at the interface, and you can see that it's very, very strong, right? So there's a field of about 2 volts per nanometer in the interfacial layer, simply because these molecules are oriented so strongly. And then we can calculate what would be the energy of this rigorously oriented H4 plus molecule in such an electric field. Yeah, so that's the dipole moment mu of the H4 plus molecule. This is the average cosine theta of the H4 plus molecule, and this is the electric field that I calculated here in the MD simulations. And what you can see is exactly this type of energy profile. Yeah, so there's a 4 kT adsorption simply by orienting this dipole in the interfacial electric field. Yeah, and that is roughly the same sort of 4 kT that you see here. Yeah, so from this argument, what we believe, and I agree that this is sort of a hand waving way of doing things. But what we believe is that it's really the enthalpy of the electric field here that drives the adsorption of the molecule to the interface. Yeah, and there are many ways in which you can look at that. You can think about hydrogen bonding or explain it in many other different ways. But simply the electrostatic energy of being in this interfacial region is very favorable for this H4 plus molecule. Yeah, that's what we believe, that the hydronium adsorption is driven by the orientation of the hydronium in the interfacial electric field. Right, 5 minutes. Okay, so then I'll be relatively quickly, because then we continue because we haven't solved the original question at all, right? So the H4 plus is adsorbed to the interface, but still these surfaces, these air-water interfaces, behave as if they are negatively charged. And there's one related problem there, which is called the Jones-Ray effect, which is if you zoom in on this graph to very low concentrations. What people did before, and this is from 1940 measurements by Jones and Ray, what you can see is that there's a non-homogeneous behavior of the change of the surface tension as a function of the salt concentration. Yeah, so there's a slight minimum here at around 1 millimole per liter, where the surface tension actually first decreases and then increases. And this is again, that this people have thought about what it could be, whether it could be any form of ion adsorption. And there are a few different explanations, which I'll just show you briefly. Yeah. So there's the surface absorption of one of the added ions. This is maybe true for iodide, but we see the same minima for chloride and fluoride. So that cannot be the sort of general explanation of these things. Absorption of hydroxide ions, which would work very nicely with the negative effective surface charge, but that doesn't work either, because the hydroxide here, yeah, so this is again the surface axis, is very negative. So the hydroxide is being repelled from the interface. Absorption of hydronium could be, but that's very weak. That's a very weak effect. This I will not show. Yeah, this is all. We did all these calculations, but I will not have time to show them here. What I will focus on is this final one. So the surface active impurities in the water. And the way we did this is together with Yuki Uematsu, is by writing down the free energy of a ionic solution at the interface. So there are the entropic terms, there are the electrostatic terms, and here is the adsorption energy UI. Yeah, now we model this adsorption energy very, very, very simply by a box profile, which has only one sort of spatial extension, Z star, and there's one depth of adsorption, alpha I, where I is the type, the ion type. And these two parameters are fixed rigorously by the experimental surface axis. So if you go to high concentrations, you can simply fit this. Right? It will give you these two parameters rigorously. So if you go to high salt concentrations, you can simply fit these curves, the experimental curves, and get out values for alpha and Z star. And then what we do is we introduce a contaminant, and there are these contaminants which we believe would be relatively common nowadays in the environment. So SDS, that's the main component of soap. Yes, so it's a long hydrocarbon tail with a sulfate head group. And there again we look at the adsorption. So this is the concentration of SDS, and again the change of the surface tension. And you can see that these things absorb very, very, very strongly. Right. So this goes down to minus 40. So this is linear, and then of course at some point you get this micelle formation. So so here it's not linear anymore. But the first bit we can fit as well, and we get out this adsorption potential. And it turns out that this thing here, this SDS, it absorbs to the interface with a interfacial depth of about 16 kT over half a nanometer. Yeah, so it's an excessively strong absorption. Now if we take that into account, so we put in some impurities, and we simply fit sort of what is the impurity concentration that we need in order to reproduce these Ray-Jones effects, these Ray-Jones measurements. And the nice thing is that you need an impurity concentration in the water of only 10 nanomole per liter. Yeah, so that's a very, very low impurity concentration. It's much lower than what most people can detect in experimental work. Yeah, so it's something that is also very, very hard to clean. So any experiments that you do, I guess it's a challenge for any experimentalist to claim that they have an impurity concentration which is below this threshold. So that reproduces this surface tension minimum. Does it reproduce the rest as well?
How big is your sample? How many molecules do you have in your sample?
This is purely analytical work. So there's no sample here, because this we cannot do in MD simulations, right? At 1 nanomole per liter.
That's exactly
right. Yes, exactly. So this is purely a continuum model. So we do this on paper, in fact. So yep. Right. So there are a couple of other measurements. So the first one that I showed, right, is electrostatic mobility. And there are calculations or measurements done by in a group of Regine von Klitzing, where they measure the disjoining pressure between an air-water interface and a actually negatively charged silica layer. Yeah, so here this is a picture I took from another paper. So here it says it's positive, but it is a negatively charged layer. Yeah, what you can do is by measuring the pressure here that you need as a function of the width of this layer, you get these disjoining pressure curves as a function of the distance between the silica and the top of this air-water interface. Yeah, what you can see is that this is positive, so these surfaces repel each other, which means that the air-water interface must be negatively charged again. Yeah, so it behaves as if it's a negatively charged surface, and it's the usual sort of decrease as a function of the position. And we model the same thing, and we used exactly the same model as what we used for the Ray-Jones effect. And what you can see that with a nanomolar range impurity concentration, we can actually reproduce these data as well. Yes, we have this very strong absorption of a very tiny amount of impurities, which actually gives reproduces this effective negative charge at the interface. Yeah, and then finally, going back to where I started, This electrostatic mobility of the particles. This is the zeta potential, so that's a sort of a recalculation of the electrostatic mobility using a Douwe-Chapman model. You can recalculate that in terms of a potential at the interface. So negative potentials mean that the particles move in the direction of the positive electrode. Yeah, so that's what we see for air bubbles. This is a function of pH. You can look at the data here. So at neutral pH, this is negative, which is roughly that's what I showed you initially already. And this is for different salt concentrations. And again, we try to fit this with the same model, the same box profile model of a tiny amount of impurities. And again, we can at least qualitatively reproduce also this data using a nanomolar concentration of impurities. So with that, I will briefly show you my summary. So dipolar order does not induce any electrostatic mobility, no matter who claims otherwise. Protons do adsorb at the air-water interface, because that is shown in the experiments already. Right? It's very, very hard to explain the vast set of experimental data that people have measured over the past century without assuming absorption of protons. And here we can show that also from a molecular point of view, you expect protons to adsorb. And finally, these effects, this Ray-Jones effect, yes, the small minimum in the surface tension, the disjoining pressure, and also the electrostatic mobility can actually be explained by using this tiny amount of impurities in the system. So with that, I would like to thank you for your attention, and I'll be happy to take any questions.
Set up, and we can take questions while that's happening. Any more questions?
How do you think the picture could change if you were doing the experiments in liquid crystals?
So with these methods, I think I don't have the scale to actually look at that in this sense. So that's but it's a very nice thing to think about, and it's yeah, it would be very nice to discuss this in more detail. Yeah.
In your Campanello, whatever it was, the ab initio that you used.
Yep.
How big a sample could you use? How many molecules?
So this is a total of 256 water molecules.
156.
Yes. Yeah. It's relatively big. Yeah. Yeah, it's relatively big, but it's.
Campanello or method did you use?
So this is all. We can discuss in a bit more detail. Yes, it was done. So the calculations themselves were done by my collaborator, Christopher Lolio, and this is but it's a relatively big sample. Yeah.
Okay, let's thank you again for a nice talk.
Thank you.